Hello everyone, welcome to another physical science lesson. Today we're going to be continuing our investigation on electromagnetism, and in particular we're going to be looking at something very interesting. We're going to be looking at the magnetic field that you find around a loop or a coil. So let's go and have a look at what we're going to be discussing today. So if you look here, magnetic field around a loop or around loops and coils, I wonder what that might be about. And so as we look over here, we're particularly looking about an electric current that passes through a loop. We're looking at an electric current that passes through a loop. So the current passes through the loop, and we want to say, well, what's the magnetic field going to look like if it's passing through a loop? And later we'll look at a coil and say, what's the magnetic field that is around a coil? Right. Now, have you ever thought about what might change the pattern of the magnetic field around a conductor? And how could we change it? Maybe there'd be a different sort of pattern shape around a loop or a coil, and that's what we're going to investigate. But is there another way of thinking about changing this pattern that we get around a conductor? Well, you think about it and maybe we'll answer it as we go along. So the question that I want you to think about is, how can you change the magnetic field around a conductor? Different ways of changing it. So we want to just quickly revise some terminology that is common in this section, namely the right-hand rule. I hope you can remember what that is. Remember, you take your right hand and you're going to show the direction of the current using your thumb. So if the current is passing up, then you point the thumb up. If the current is down, you point the thumb down. And then what do you do with the fingers? The fingers give you the curl of the direction of that circular pattern around a straight conductor. We're going to use that and see what happens when we do it on a coil too, or on a loop. We're going to talk a little bit about the magnetic field strength. How do you know the difference between a strong field, or region where the field is strong, and the region where it's weak? How can we represent that? And here's a new term, magnetic flux. Let's have a look at each of those terms. So I want to start off by just revising the use of the right-hand rule. We're going to do this quite quickly, but we must make sure that we understand it. So let's go and look at that experiment that we've done before, simulation of the experiment at least. We're going to look at the field pattern and the direction of the field when we current passes through a conductor. And so let me have a look at this particular simulation, and here we go. Now you'll remember that we can see these iron filings. They're kind of in a pattern, but it's not a very convincing pattern. But there's an opportunity here to change the intensity of the current, to change the strength of the current. And if you look at that pattern, it's even more scrambled. So if we increase the current, look what happens. It becomes more defined. And if we increase it a little bit more, it jumps and it forms this nice circular pattern. So clearly by increasing the current, we can change the pattern. But one of the other things we could do is we could change the direction of the current. Now the pattern doesn't change, but what does change? Have a careful look. Look, the direction that the compass needle was pointing in changes. And I want to just make sure we've got that in terms of using the right-hand rule. So when the direction of the current over here is going from positive to negative, and we recognize then the current is going down, can you see that the thumb points down and the curl of the fingers is in that clockwise direction? Whereas if I change the direction of the current, it's now going up and the direction of the field is in the opposite direction. So we need to recognize that changing the current strength changes the direction, changes the intensity of the field pattern. Changing the direction of the current changes the direction of the magnetic field. But what's important here is that in both these cases, the magnetic field is still perpendicular to the direction that the current is passing through that conducting wire. And so you recognize they're perpendicular to each other. Now, if we go to the next slide, we recognize that we've said the magnetic field, the strength of that magnetic field is called magnetic field strength. It has a symbol B, which is measured in Tesla. We're not going to do too many calculations with this. It's just a measurement of the strength. And we recognized when the pattern, when those iron filings are closer together and they're all clustered together, that means the field is stronger. And we're going to be looking at that in a little bit more detail. Now, if we were to represent this magnetic field around a straight conductor, we use dots and crosses, and we use this notation, again, just showing the right-hand rule. If you take a look, you'll recognize the direction that the current is going is from positive to negative. So the thumb points in that direction. And look at my fingers. They're going into the board over here. That's why there are crosses there. Whereas on this side, as I'm pointing in that direction, can you see my fingers are coming out of the board, and the dots indicate the direction of that field. The dots are saying to me the current is coming out. So it's that circular pattern that we've seen before in terms of where the magnetic field is. So if we wanted to recognize the strength of the magnetic field, where is it stronger? Well, where the dots are closer together. And I've drawn a little area, a little square, to say this magnetic field is passing through an area that I selected. And there are lots of field lines that are parallel to each other that are passing through this area. So they're kind of clustered together. There are lots of them per unit area. It's kind of like a density idea. The more there are in a certain space, but it's not density, because density would be mass over volume. This is the field strength divided by area, and that area is at 90 degrees to the field lines that are coming through there. So we'd recognize when they're close together, there is a strong magnetic flux. There are lots of field lines in a small area. And that's a new term. It's a relationship between field and area. Now look at the same area over here, and you'll see the square that we're using is exactly the same size and shape, but we've got far fewer field lines passing through it. So the magnetic flux is weaker. The important thing about magnetic flux is not only that it's the field strength times an area or per unit area, but we're recognizing that it is that area is at 90 degrees to the field lines. So let's formally define magnetic flux. So magnetic flux has an interesting symbol. It's this strange looking Greek letter, which is called phi. You might have heard of pi. This is phi. Quite similar, but just a different shape. And you need to be able to recognize how to draw it and to make it clear. Now, the formal definition, or the equation that we use to define magnetic flux, tells us that it's the product of the magnetic field strength and that area. Remember, that area that is at a normal, or in other words, normal to B. In other words, at perpendicular to B. Now, this angle here causes people some confusion. If for some reason you have a strange magnetic field that might not exactly be passing through an area at 90 degrees. Say we examine a situation where the field lines are passing through at an angle. They're not at 90 degrees. Then we will have to take a look at making it the difference in the angle between the normal and the area. So this angle theta is the angle between the normal and the area. So theta stands for the angle between the area and the normal. So it's a component, if you like, of the area that needs to be at 90 degrees. Because at 90 degrees, that's where it's going to be the most effective. It's the best way to compare what the actual flux is. Because if it's just hitting a little bit, well, we'd not get a good idea if the area wasn't exactly right. So the unit here is called a Weber, and the symbol is WB. Right, guys, that's the beginning of our little introduction to what happens when we look at loops and coils. Take a short break. We'll be back after this. Welcome back from that ad break. I hope you've had a bit of something to relax and think about, the questions we've been asking. Remember, the one question we said right at the beginning is how can we change the magnetic field pattern? And hopefully you've got some ideas already. And to put it more formally, we can say, how can we change the magnetic flux? Well, here are some things to consider as we're looking at changing the magnetic flux. We could say that we could increase the current. And you've seen that the pattern changes, and if the pattern changes, that means the field lines would be better. Would be closer together. We'd also could increase the thickness of the conductor. We put, in other words, reduce the resistance. If we had a thicker conductor, we'd have a stronger current, and we could also change the shape of the conductor. Remember, we could change the magnetic flux in terms of its direction by changing the direction of the current. Let's investigate this idea of changing the shape. And the first shape we're going to do is simply to say, let's bend the piece of wire. Instead of being a straight piece of wire, let's bend it into a loop. And so here's a picture of a simulation where we're going to investigate the magnetic field around this looped wire. Now remember, we've got in this position over here the positive, here's the negative, so we know that the current is coming around the loop in the direction that I've indicated in those blue arrows. Just to make absolutely sure before we go and look at the simulation, let's check out the right-hand rule to make sure that we've got it right and to see that these compass needles are pointing in the right direction. So we point the direction of the current is up like that, then you'll turn the fingers, and as you can see, I hope you can see, that these little compass needles are pointing in an anti-clockwise direction, just as we would predict. Whereas if I go to this side and I say now the current is coming down, then the needles are pointing in the other direction, it's going clockwise. So that's quite an interesting observation in terms of applying the right-hand rule and seeing what the effect is. But you know what? Let's go and investigate. So here we have the application, and there are a couple of things that we can do. We can, first of all, recognize what happens if we change the direction of the current. Now, look, the needles all changed. They're now pointing in the opposite direction. And if we were to look at what's happening to the right-hand rule here, you'd see that we can actually move this right hand along here, and in that position, you can see that the current is going upwards, and the circular green lines are showing you the same direction as the red compass needles. If we move it around, this magnetic field is all around the loop. It's not just in one position. It's everywhere along where that wire is. But we're just showing that the different direction is where the lines are separated by going through this cardboard surface. Now, I'm going to take that off. I'm going to say, let's adjust the position of the wires. So what do you think will happen to the compass needles if we move the wires closer together or further apart? Well, let's try it. So if we move them further apart, you'll see the loop's got a whole lot bigger. And in the middle here, some of these compass needles are starting to align, but some of them aren't quite as aligned. If we bring them closer together, you'll see that there's a stronger field in the middle here. More of those compass needles are kind of pointing in the same direction. It's not as clear as I would have liked it to be, but anyway, that's a little bit of an investigation. So now that we've looked at that, let's take a different view of it, and let's just slow down and have a look at how we represent this magnetic field around a loop or bent piece of wire. So I'm going to take different viewpoints. And the first viewpoint I'm going to have, I hope you can see, is just a half coil. It's a half loop. And we're saying that from the positive end where at this point it's positive, and we recognize that the current is going from the positive to the negative as indicated by both the blue arrow and the white arrow. And so we've got the direction of the current. But what do you think the direction of the magnetic field is going to be? And how do you think we could find it? Well, the answer is easy. You're going to use your right-hand rule. You're going to say, let the thumb point in the direction of the current. Curl of the fingers is going to give you the direction of the magnetic field. Now, I've done a little bit of preparation for this because I didn't want to be drawing too much. And what you can see is that on the outside of this loop, the field lines are coming out towards you. So they're coming towards you. The fingers are pointing towards you. But if I use the right-hand rule over here, for example, you can see that they're going into the board. And over here, they're going into the board. And if I do it on this side, where the current is going down, it's going into the board. And that's why I've put all these crosses on the inside. Now, notice the difference in the field inside the loop and outside the loop. Outside the loop, the field lines are non-uniform. They're quite spaced out. They're separated. They're just like we had with the straight piece of wire. Those that are the field close to the piece of wire, quite strong. Far away, weaker and weaker. But on the inside, there's an overlap between the ones that are far away from this end and the ones that are far away from that end, and they've kind of clustered together. And so what do you think we can say about the magnetic flux? Well, let's have a look. And I hope you can see that I've drawn the same red square. And if you look carefully, you'll see that there are lots of field lines inside that area. So this is an area of high magnetic flux. Whereas if we go to this point, you'll see that here it's low. Over here, it's high. So this tells us that this is a strong region of the field, and this is a weaker region of the field. And that's quite important. Where it's strong, all the field lines are pointing in the same direction and they're tightly packed together. It's a more uniform field. And it doesn't matter where you are within that, you'll feel the same, experience the same sense of the magnetic field. Whereas outside the loop, on the outside, it's weak and it's not going to have as much of an effect. Now, I wonder where we've seen something similar to this. Can you think about where you've seen field lines clustered together and they're quite dense, and where you can see them spread out? Well, maybe this will jog your memory. If we go and have a look at our bar magnet, what you'll recognize around the pole, the North Pole, looking your eye over here, the field lines are all coming out. That's why we've got those ones. And over here, if we look over here with the eye, we'll see the field lines are all going in and they're clustered together. That tells us this is strong. And where they're strong, in terms of the magnet, we say that's a pole. If we add to the field lines on the outside, you'll see they are spread out. And that's exactly what's happening here. So what I'm trying to illustrate for you is what we saw earlier around a coil is very similar to what we see around a magnet. In fact, if we compare these two pictures, then I would reckon that they're almost identical, and that the view that I'm having from this side of the magnetic of the coil is actually to suggest that this is a south pole. That part of the loop is actually behaving like the south pole of a magnet. And that's quite interesting. So if we go back to our original diagram, what you'll see, the compass needles are all pointing away. And that tells us that this is the North Pole. And sorry, this is not the North Pole. The North Pole is the red part, and this is the South Pole. And so we've got a very good picture of what's happening when we put a current through a loop. We're forming something that, while the current is passing through the loop, is very similar to a magnet, a bar magnet. And that's why we call this type of arrangement an electromagnet. It is only magnetic while the current is passing through the wire. Now, obviously, it's not a very strong electromagnet. And what we're going to need to think about is how can we increase the magnetic flux to make this a stronger electromagnet. Now, I'm sure you've done some experimenting with this, and we're going to take a look at it. But first of all, let's make sure that we understand exactly what's happening here, and you draw the pictures so that you've got a very clear understanding of the magnetic field that we observe around a loop. Hi everyone, welcome to this physical science lesson again. We're exploring electromagnetism, and in particular we're looking at what the magnetic field pattern is around a coil. So have a look exactly what we're doing here. So what is a coil, and what's this word solenoid? It's an interesting word. And we just need to make sure that we understand that a coil just means that we've taken wire and we've wrapped it around something. And a solenoid is exactly the same as a coil. It just means that they're used interchangeably. A solenoid is just wire that's been wrapped around an object. That object could be a piece of plastic, a piece of wood, it could even be an iron nail. And that would give you the idea of what a solenoid or coil is. Now, the reason we're looking at this idea of a coil or a solenoid is we started in terms of looking at the magnetic field around a loop. And the first idea that we had was to look at the side-on view, where we recognized, using the right-hand rule, the current is going in this direction, so we could draw little crosses going in over here to represent the magnetic field inside there, and we'd recognize on the outside they're little dots, and they're not as evenly spaced, and they're far spread out from each other. And in fact here, this we said was a south pole, because it looked exactly like the field line pattern of a magnet. Now, just to understand what's happening here, we're wanting to do a little bit of a thinking observation. And you might be wondering, what are those round orange circles with a dot and a cross? Well, I want you to imagine what would happen if we took a piece of a very strong saw and we cut that loop in half, and we cut it in that sort of where the red line is. And now we started to use our eye and we looked from the top. Then looking down over here, we'd recognize, hold on, at this point here, from the positive, the current is coming up over here. So we've represented the direction of the current in that position as a loop with a dot in the middle. But over here, the current is moving down. So we've represented, the eye would see the current going down. It's going into the surface. So we're looking down on it, and that's why we'd have it as a cross. So take away the middle bit, and we have our dot and cross. And this is just another view of the magnetic field around this loop, this conducting wire. So how could we represent what's happening? Well, you know what? Let's just use our right-hand rule. And by this time, you should be getting lots of practice. Recognize the thumb points in the direction of the current. So into the board over here it goes, and we loop it around, and we can see that it's got a curve that's going around like that. I've drawn them in, and you've seen this before. These circles that are representing the field lines, notice they're not evenly spaced because this is a non-uniform field. They might actually change a little later on when we have the current moving there, and my diagram might not be as accurate as it should be. These might be pushed a little bit closer together. But if we were to say, so what's happening on this side, we use our right-hand rule, and we say, well, it's going to go down on that side, and it's going to come, it's coming out, so I'll go and stand on this side, it's coming out of the board, and it's going up. So if we now look at my diagram where I've added in those circular field lines, we recognize something very interesting is happening. In the middle here, between these two pieces of wire, the field lines are pointing in the same direction. They're all aligned. They're going in the same direction. They're bunched together, and they're all packed together nicely. Over here, they can spread out. So these ones should really be more uniformly spread. And the overall effect is that there's a very strong upward push or direction of the magnetic field. The magnetic field is very strong between these wires, and we indicated that by the big blue arrow. Now, in which direction does the magnetic field run, or between these wires? Well, let's take a look at the pattern. We'd recognize it's going up over here, and then it's going down over here. It's going up over here, and it's down over here. Does that pattern look like something that you might remember? Let's just draw those lines overall so we can get a sense of it. Something that does that, and going like that, and going like that. Does that ring any bells in terms of this sort of butterfly type shape? Well, of course it does. It looks just like the bar magnet. So we're not surprised that when we said that loop, when we looked at it end on, we saw all the field lines pointing, going into the board, and that they were similar to the South Pole. Well, it's absolutely, because this is where we were looking from. Our eye was looking from this position, which is the South Pole, and this position is the North Pole. Let me illustrate that a little bit clearer so you can see that point where the field lines, they're coming out of the north on the outside of the bar magnet or of the electromagnet, and they're coming in at the south. On the inside, between the wires, we see that they are running from south to north. On the outside of the wires, we see that they're running from north to south. So just like a bar magnet. And guys, that is a very important idea for us to get together. That it doesn't matter how many ways we look at this. The loop is, hopefully I've convinced you, an example of an electromagnet. And so I've put the two drawings together, and you can see absolutely that they are mimicking each other. They have the same sort of thing. Although they look very different, don't get mixed up now from where you're looking at. This is kind of the top view, and this is the side-on view. They look different, and the notations that we're using are different, but they're describing exactly the same thing. Just to make sure that you've got it, let's have a look and make sure that you are very clear that this is exactly what's happening in our loop. And if we go to our simulation, which we had, or the diagram of our simulation, which I'm just going back to over here, you'll see that's exactly the same thing. We recognize that it goes from south to north, and it's formed this electromagnet. Let's take a quick break, and after this, we're going to see what we can do to increase the number of turns to make this not just a single loop, but multiple loops that will make up a coil. What effect do you think that's going to have? Well, think about it while you have a break. Welcome back. Let's now go and have a look at what's happening to a coil. Something interesting as well is that we have another rule that we can use to find the direction of the magnetic field around a coil. This is called the right-hand solenoid rule. So we've done the idea of what a coil is. We're going to be looking at this idea of the right-hand solenoid rule. Now, to really explain this, it's a method to find the north pole of a loop or a coil. Now, we've already established that when we looked at the loop, that it was an electromagnet, that it has a north pole and a south pole, and we looked at the one end, which happened to be from this end, and we recognized this is the south, and that over there is the north, and you see that. So what is this thing called the right-hand solenoid rule? Well, it's kind of different, and it's quite interesting because it's quite useful to use. We don't have to use the ordinary right-hand rule in lots of different places, but we can simply use the right-hand solenoid rule directly. And so the way that it works is we're going to switch things around a little bit. Usually in a coil, we'll have more than one piece of wire. So we'll say there are many fingers on my hand, so that will indicate the direction of the current. Even when I've got a loop here, we'll take the direction of the current not to be the thumb this time, and if I do that, then you'll see that the curve of the fingers gives me the curve of the loop. So as I can say it's going in that direction, I'm showing you the direction of the curve of my fingers. Now the thumb here, if I turn it, you'll see the thumb is pointing in, and the end of the thumb always indicates the north pole. So if we do it next to the board here, you'll see that we're going around like that and we're pointing in. This side was the south side. The red arrows of the compass needles are pointing north. So the north side is on the other side of the loop. Let's have a look and apply that to this diagram. We recognize exactly the same scenario. The direction of the current, it's coming out of the board over here, it's going into the board over here, and guess what? It's pointing to the north pole. Isn't that amazing? So the right-hand solenoid rule works. We've seen it in two situations. And here's the third one. And we recognize that this end we called the south end. Let's make sure that it's working. We take the curl of the fingers to show the direction of the current, and the thumb over here is pointing in. That means this side is not the North Pole. This side is the South Pole, just like we've confirmed it over there. So guys, this is an important rule that we're going to use as we investigate the magnetic field around a coil. So let's have a look at a simulation. And here's the simulation. I just want to point out that the coil here is wound in a particular way. The wire over here, that's the positive terminal, that's the negative terminal, and you can see the wire is coming on top over here, and it's coming around in that direction and goes around in the back end there. So the direction of the current would be up on this side, it would be up on that side, it would be up on that side, would be up on that side, would be up on that side. And so we can start to apply the right-hand solenoid rule. And if you look at it, you recognize many wires. They're all pointing in that direction. The current is pointing in the direction. Where's the North Pole? The thumb is pointing to the North Pole. I'm saying the North Pole is there. That means the South Pole is there. Now, does this line up with what we've said about north and south? Well, absolutely it does. Look at that. The red arrows of the compass needle are all pointing away from the north, and they're on the outside, they're pointing in towards the south. And it gives you the butterfly configuration. They're not crossing over. They're recognizing that they're going in that lovely pattern that is exactly the same as a bar magnet. No wonder we call this an electromagnet. Well, let's go and do a little bit of playing now that we've done that. And here we've got some options to be able to change things around. The first thing that I want to do is I want to look at this pattern and I want to say, so what would happen if I change the current? So let's switch the current, and lo and behold, what can you see now? You can see that at this point here, the red arrows are pointing away from this side, where they're pointing in on this side. Switch the current again, and you'll see that on this side, they're pointing in over here, and they're pointing away over there. That's quite interesting. Now, to make it absolutely clear and plain, let's replace the compass needles with some field lines and represent them with arrows. And so what can you see? You can see these green arrows are pointing in at this side, and they're pointing out on that side. So if we use the right-hand solenoid rule, recognize that the current is going to come in on this side, going up at the back over there, and it's going to come around. So which is the North Pole? The North Pole is in that direction. Now, just to confirm that I've got it right, let's use the big hand over there so you can see the graphic. The wires are wrapping around in that direction, and so we can see the North Pole is pointing in this direction over here, that you can see where the thumb is. Now, the other option that we've got is to change the way the wire is curled. So if I switch the coil, and I just take the right hand off for a minute, it might not look like much has changed. But in fact, a lot has. The wire is going in a different direction. And that means the current is going in a different direction. The one time it was curled clockwise, and another time it's curled anti-clockwise around this particular cylinder, depending on which side you're looking at it. So if I'm looking from this side, you'll see the wire is turning in that direction, which is clockwise. If I'm looking from this direction, the wire would appear to be anti-clockwise. But so you can change the wire, and it's important that you look at these diagrams very carefully, because changing the way the wire is wound changes the direction of the field lines as well. So if I've changed that, have a look. We're going to say the current is in that direction. This is the North Pole. This area over here is going to the north. That is south. We use the compass needles. Have a look. North, the reds are pointing in that direction. We use the right-hand solenoid rule. And no surprise, we've got the North Pole at this end. Guys, this is an important thing that you need to practice. And these simulations are great. Make sure that you get a chance to use them for yourself if you can. So, we've done a little bit of an investigation, seeing how this can change and the effects of the magnetic field. I want to have another look at the representation of the magnetic field around a coil. So the blue area here just represents a rod. It could be an iron rod, it could be a plastic rod, it could even be some cardboard. And what it's showing us is the way that the copper wire is around this particular coil. So what it's saying to us is on this side, all of these lines, the current is coming out of the board. It's coming out. And on this side, it's going in. Gives us the perfect opportunity to use the right-hand solenoid rule. Check it for yourself. Take a moment, hold your hand in the right position, and you recognize that the fingers are going to come out over here on the right hand. They're going to curl in and go over there. Then this must be the North Pole, and that must be the South Pole. So how would I represent the field lines? Because that's what we wanted to show, is not just which is north and south. We want to actually show the direction of the field lines. We've shown the direction of the current, but let's show the direction of the field lines. And what we've said, every time we draw field lines, we recognize that they follow the same pattern. They come out of the North Pole. Little compass arrows would point away from the North Pole, and they would be attracted to the South Pole. On the inside of the coil, they'll be running from south to north, and those would line up. On this side, we would find that the field lines do exactly the same thing. They run away from the North Pole, they run towards the South Pole, and we've got a complete loop. Now, guys, that's not the end of the story, because what we've got to recognize is there are far more field lines, and this idea of a pole indicates that there are many more lines that would pass out. So we'd have to draw those in, but try and not get them to cross over like I've just done, because it's a little bit difficult on this board, and we'd recognize they're coming out of the north and coming in at the south. So practice drawing your field line patterns, particularly around a coil. Get used to looking at them at a different view. In this case, we're looking at a top view. Now, how else do you think we could look? Is there another orientation to look at a coil? Well, yes, there is. Let's imagine for a minute that we put our eye at this point over here. What do you think you would see if you looked directly at the end of the coil in that position? Maybe you'd like to even just take a piece of paper and sketch down what you might find. But don't wait too long to do it, because I need to move on. And I'm going to say, this is a representation of a coil and the magnetic field associated with the coil. What I haven't indicated on the diagram is the direction of the current. So I've got to interpret this field line, and I've got to be able to say to myself, is this a North Pole or is it a South Pole? How would I know the difference? Well, remember what we've just done. We've said at the North Pole, the field lines run out of the North Pole. They're coming out of the North Pole, and they're moving around the magnet. On the outside of the magnet, or the outside of the coil, they're moving away from us. So on the inside of the coil, they move towards us. On the outside of the coil, they move away from us. And what have we got here? On this side over here, these magnetic field lines are coming out of the board, and over here they're going in. So over here they're going out, and on this side they're going in. So my conclusion is that my view over here is definitely a North Pole. So if it's a North Pole, in which direction is the current passing? Well, let's, at this point, pretend that this is the wire that's in front, and let's say that's the wire that's at the back. And we're going to say that in this case, and even if we looked at it the other way, it would be the same. This is the direction of the North Pole. This is the North Pole. So we use our thumb as the North Pole. Remember, the right-hand solenoid rule. And the wires are curving around that way. So over here, the current is going up over there. It's going around over there. It's going around over there. It's going around. And eventually, it goes back out that way. And so we've been able to see the direction of the magnetic field as well as the direction of the current. So if we're going to change the field, we recognize we could increase the current, we could change the direction of the field, we could also increase the number of coils. And if we look at that, we recognize that electric fields have an important part to play in our environment. We have power lines, lots of current passing through the power lines. Current isn't very big. We use transformers to reduce the current. But these still have an electric field. Do they affect things? Well, the research about affecting humans isn't very evident, but we do know that many birds who navigate with magnetic fields do crash into these. And it could just be that they are very big birds and they think they can land and then they get shocked, or they could actually be navigating towards them. We're not sure. Quick summary. Remember that the magnetic field around a loop is similar to a bar magnet. We use the right-hand solenoid rule to find the direction of the North Pole. And we can also use crosses and dots to show what's happening to the field lines. Please make sure you practice these. And don't forget that you need to always revise. So it's been great investigating this topic with you, and we'll see you again soon.